The next stop that we will come to, we'll be talking about bringing precision to nitrogen application and measurement. And when I think about this, I think about all of our old drills that we use to seed wheat and soybeans, right? What's the joke of what a drill is? And controlled spill, right? So when we think of anhydrous and when we think of 28 and when we think about how we make these rate determinations, are we truly delivering a precision application of those products? So show of hands, just so I can tell Josh at the next stop, how many folks use anhydrous at home for your nitrogen? Okay, not quite half, so quite a few of you. The question becomes, we're taking, back to sixth grade science, right? Are we a liquid or are we a gas in that tank of anhydrous that we're applying? And then our whole idea and what we lovely call our task that day, we're rolling smoke, right? Or we're applying gas. But what's the ironic part about that? Anytime we see gas, what happens to our nitrogen? We've lost it, right? Our dollars are heading off into the atmosphere. So how do we as growers take a liquid under high pressure, turn that into a gas, inject it into our soil, and truly capture every dollar and every cent that we're putting in? So Josh Messer and Greg Ury will talk a lot about how we get that nitrogen applied in terms of anhydrous. And then, in the earlier session, we talked a lot about mineralization. So show of hands, everybody be honest. How many decreased your nitrogen rate by about 100 pounds this year? Got one guy, right? So the question becomes, we have a year as last year. And when I think about the years, keep in mind I'm talking about Indiana, Michigan, and a little bit further north and east. Last year, if I categorized the year with one word, it was a flood. Okay, move forward to 2016, and if I categorize our year as 1 year, categorize it as a drought. And when we think about this level of mineralization that we're having, we're not having all the loss mechanisms that we did to that nitrogen the year before, and our mineralization rate is a lot higher. Greg talked about that. So in terms of I'm not losing it, my soil is making more. 100 pounds for most of you might be a little bit extreme, but if we're not differing our total nitrogen rate by about 50 pounds, did we do the right thing? Did we over-apply? That last slide that Greg showed, about we've applied, I think that last slide was like 70 pounds more nitrogen applied, but it did not increase our yield. So our NUE on one side was 1.01, but our NUE on the other side was 0.7 pounds of nitrogen to make that next bushel. So when we think about nitrogen application, we think about what we're trying to do by differing our schemes. The end result isn't, well, I applied 50 more pounds of nitrogen and I made X number of bushels, right? That's not what it's about. It's about taking that same pound of nitrogen that we're applying and being more efficient with it. Or perhaps we take a little bit closer look at our total nitrogen program and we say, hey, I'm planning on 40 pounds of loss and I'm over applying 40 more pounds now that I'm being much more efficient with every unit that I'm putting out there. So this next step, is all about loss prevention. Okay, we're managing that, and we're trying to hit the year with exactly what we need. Southern Michigan last year, where we farm, we had fields, strip trials that went 225 bushels an acre. Okay, that's extremely high for us. If you guys know anything about Michigan growing conditions this year, there's going to be a lot of folks be lucky to get 150. And when we go back and we think to that barrel and stave concept, that lowest stave in the barrel is where our water runs out. That lowest stave in the barrel is what determines our yield potential. Last year, where was that bottom stave? It was really high for me. This year, that bottom stave, where is it? It's a lot lower. So when we think about, did you apply 100 less pounds? That might be dramatic for some of you, but when we take in consideration all of these factors, that's an ongoing process. Every day it changes throughout in our growing systems. Can we be there? Can we be more efficient with that?
All right, welcome everybody. My name is Josh Messer. I am the Ag Retail Specialist for Western U.S. I also cover the Nebraska territory as a Regional Agronomy Manager. And with me today, I've got Nowell Moore. He is Product Engineer for 360 EQUI-FLOW and pretty much anything else they ask him to do. The engineers do a pretty good job of jumping back and forth on projects. They stay pretty busy. Also with me, I've got Jason Kienast. He is our research agronomist here. A lot of the work and efforts that you see done out here at Proving Grounds is large part to do with Jason and his team. So I commend them for a great job and putting on a great show for you guys. And we also have Greg Ury. Greg is the Regional Agronomy Manager in Southern Illinois, Delta. What other states you got? Kentucky. He gets around a lot. So guys, unfortunately, this is going to be one of the stops where we do not have a live demonstration. We figured anhydrous ammonia live demonstration is probably not the best interest of your health. However, we did ask the neighbor to come out and do a little raking of hay so you can see some equipment moving. Anyway, so what we're really going to focus, guys, is we're going to focus on that accurate base plus system followed by a measurement. So you heard Greg talk about it. In order to get to that profitable level at today's input costs and at today's commodity prices, we've really got to become more efficient. So how do we take advantage of what Mother Nature can give us, or how do we manage against the risk that we could get in years like 2012, where I don't overspend and I don't waste that money and not get the return on investment? So a Base Plus program. Base Plus should be about 40 to 60% of your planned nitrogen needs. In most cases, that's going to be enough to get you out to that V12 application, so it gives you a very wide window for measuring and knowing when to get out there and start side dressing. But when we do those Base Plus programs, guys, we've got to remember we've got to stabilize that base approach. We cannot allow Mother Nature to start washing that nitrate nitrogen away. So we've got to stabilize it to make sure it stays in ammonium form as long as possible so that we can get that extraction. But what we also got to look at is we've got to focus on precision placement. And we've got to make sure that we've got the right amount that goes out there across all the toolbar. The closer we can get our seed zone to the application of nitrogen, the higher rate of recovery we're going to get. We don't want to rely on Mother Nature to wash it into the rooting zone, but on the flip side, we also don't want to, we want to make sure that we're not hurting our seed emergence with injury. But the other thing about it is constant measurement and monitoring. If we're going to start lowering the amount of nitrogen that we're going to apply up front, we've got to make sure that we're out there knowing what's going on in our fields. Are we getting hit by carbon load? Are we starting to leach because we've had too much rainfall? Do we have saturated soils and we're losing it to denitrification? Jason and Greg will touch on that when we get the SOILSCAN, the importance of measurement and what it can teach us. So we look at a systems approach versus a one and done. Stephanie, I think this is your picture from last year, is it not? This is your picture from last year. So in that bottom right corner there, we've got a one and done program. So we've got a lot of corn in that field that's having a bad day. Versus that systems approach over on the left. The corn is much more even, we're on pace, we're maximizing yield potential, and most likely we've got a lot higher profitability because we probably lowered our amount of nitrogen we need, so we took advantage of that monitoring and measuring. So we want that corn to live in a good day every day. It's not always possible, but that's what we're trying to do today, is teach you about the tools that you have at your disposal to maximize your efficiencies. So Base Plus with anhydrous ammonia. How many people on this tram are actually doing anhydrous ammonia today? Quite a few. Perfect. How many of you are in that one and done scenario? Couple. All right. How many are side dressing anhydrous ammonia? All right. Get a feel for what we've got here. So Base Plus with anhydrous ammonia, guys, a very good program. Fall versus spring. Jason, you've done some work here this year. You're seeing that that spring applied is actually releasing a lot later into the season than even a fall application with a stabilizer. So that's very interesting stuff to look at, but why do we use anhydrous ammonia? Well, number one, it is that stable form. When we put that in the soil profile, it's going to convert into ammonium form and it's going to latch on to your exchange sites. So we've got a 20 CEC. What's the rule of thumb? Take it times 10, that's how much nitrogen we can hold, correct? So if we got a 20 CEC, we can hold 200, but that doesn't mean it's going to hold 200 the whole way through, right? As our soil temperatures increase and we get into that 60, 65 degrees, that conversion is going to start to happen pretty rapidly. As that happens, we're usually hitting V4, V5 stage, and how much nitrogen do we need at that point in time? Not a whole lot, 5 to 6% of that crop's need. So now if we're in that volatile nitrate form, we can leach it, denitrify it, and it can outrun your rooting zone of your corn. So we've got to make sure that we understand that process when we're looking at anhydrous ammonia. But we use it because it's also the highest concentration of nitrogen for a source. It's easier to move out the field, a lot less product to get out there, and it's the cheapest form, right? Most of the time it's the cheapest form as per unit of nitrogen. But the way we've done it in the past, guys, sometimes is leading to being the most expensive nitrogen program. If we're out there putting it all on in the fall or all on up front, we really put all the cards in Mother Nature's hands. She's going to play the game. She's going to determine how much you're going to be able to recover or how much you're going to lose. So that's why we've got to start looking at more of a base plus approach. So, anhydrous systems. Over the last 10 to 15 years, what's really changed with anhydrous ammonia application? Well, we no longer have to reach back there through the window and pull on a rope, right? We don't have to go back there and crank on a rusty dial to adjust our rate. We've got much more technology in the cab. We can adjust our rate from the cab, we can variable rate across that field. But when it comes to the nuts and bolts of that system, what's changed? Not a whole lot. The knife, the coulter, the machine that you mount it on, the cooling, the heat exchanging is pretty much the same. So those are things that we got to start thinking about so we understand what our issues are. So here's a picture from our home farm where we've got some streaking of anhydrous ammonia going through that field. We're in a strip till situation. I had variability across that toolbar. So now I've got a very difficult decision to make. As I go out there and I am soil scanning, if I'm hitting the rows that are really low, I'm probably going to end up over applying on other rows. But if I hit the rows that are really high, now I've got under applied and I can't bring that low yielding environment back up to par. So it makes it very difficult to become efficient and profitable in a situation like this when we have row to row variability. And this is what that looks like when you start to measure that. Nowell will touch a lot more about this on the bucket testing when you get over to him. So very interesting stuff that they're finding with that bucket testing. So spring applied anhydrous ammonia. How long do we want to wait when we do anhydrous in the spring before we go out there and plant? At least a week, 7 to 10 days, right? And why is that? Seed safety, as you see in the photo on the slide here. We don't want to burn that seedling as it's coming up and emerging. So this is an instance where we followed very close behind the planter, or behind the anhydrous applicator with the planter. And we actually burned that seedling and it did not emerge. So seed safety becomes a very big issue. But when we want to talk about efficiency in a nitrogen program, we've got to have placement. We've got to be near that root zone. We've got to be near the plant so we can be efficient in extraction and recovering those nutrients. And the whole reason behind that seed issue is sealing. So here's a video I took in Kentucky this spring. I'm following behind that toolbar. We just started in the field, so the knives are nice and clean. We're just doing the first pass here. You can see I'm following behind. We're sealing up really nice. That knife is doing exactly what it's supposed to do. No puffing. Seems like it's sealing very well. When I go over there and I kick one piece of dirt away from the top of that furrow, this is what I see. Anhydrous ammonia, when you inject it into the soil profile, expands vertically. So it's got an expansion zone down in that soil profile, and it's going to move up. And the poorer job that we have as far as liquid ammonia coming out of the end and less pressure or poor knife performance, the higher that's going to come in the profile, so that can lead to more issues with your seedling safety. So how do we cure that? Well, in the past, everybody has a claw hammer in their toolbox, right? You change tanks, you run around, hit every shank with the claw hammer, knock the mud off so that knife can go back and do what it's supposed to do, lift and seal. But get back in the field, 5-10 acres down, you get that condensation building up in the knife, the mud clings to it, and now you get that buildup. So now we're opening that furrow again, and we're requiring more horsepower to pull that toolbar through the field. So we've got to look at ways that we can reduce that expansion zone and seal anhydrous a lot better. And I'm pretty sure everyone here that's done anhydrous has experienced this. Getting down to that last 15 to 20% of the tank in rolling terrain, I think I can make a few more passes, right? It's just a little bit of variability on that first pass. Get over the hill, we're good, settled out. Turn around, come back up the hill. Ooh, that's a little bit more. Maybe one more pass. You get that third pass, you get pretty nervous, you lift up halfway and you go back and change, right? That's because we rely on tank pressure with conventional systems. That tank pressure is responsible for taking the anhydrous not just to the cooler that you see on the toolbar, it's responsible for pressurizing and pushing that anhydrous all the way out to the injection point. And there's a pressure drop for every so much distance in line. Engineer can share that information with you. But by the time we get to that injection point, we've got very little pressure and we have very little anhydrous still in liquid ammonia state. So when we talk about that placement and wanting to get that near the root zone, this is why. This is work done with the Iowa Soybean Association. And what we did is, on each side of that graph is a corn row. And you can see that there's 15 inches away is where the anhydrous injection happened in April. The two lines on there represent 4 weeks and 8 weeks after application, measuring with SOILSCAN and finding where are my nitrates at. And they're still in the middle of that row. They drop down a little bit in that 0 to 12 profile on that 8 weeks past. It's because we've got more conversion happening and it's pushing down in that profile. In order to get higher rate of recovery and improve on that nitrogen use efficiency, we've got to think about placement even when it comes to anhydrous ammonia. So here's an example that Jamie Brand did this year out in Iowa. So you can see this is a fall application of anhydrous ammonia. You can see the streaking going through this field. And usually, yeah, that turns around. We don't see that yellow and greening streaking across that field. But what does that actually look like up close? So what Jamie did is he went out there and he dropped his core board down there and he was measuring every so many inches across. And when he hit that knife band, that elevated amount of nitrogen, he pulled a plant. And you can see that over on the far right. Got a V7 corn plant, nice and lush green. And then once he got off there and he found a yellow stunted plant, he pulled the nitrates and found that there's very low levels. And you can see the difference. We're at V6 with those plants. So that talks about how placement matters. Even with base rates up front and anhydrous ammonia, we've got to make sure that that plant can reach those nutrients even when it doesn't need a whole lot. V6 to V7, we're in that 8 to 10% needed by that time. That V6 corn plant, guys, has actually got nitrogen deficiency showing on the leaves. So that is essentially able to access zero nitrogen. So placement still matters even though that plant does not need a whole lot at that time. And here's a close-up of what the root structures look like. Larger, more robust root system is going to lead to better health later on, more water and nutrient extraction. So as we look back at those graphs, if you notice the bottom was the 12 to 24. What we were finding is in that nitrate band, we were finding more nitrates in the 12 to 24 than we were the 0 to 12. Now if we think back to what this winter was like down here in the I-States and the Corn Belt, abnormally warm, very wet, we actually had that conversion happening this winter. So when spring hit, we thawed out, moisture started moving, the nitrates were moving with it. So essentially this corn crop is not able to keep up with the movement of nitrates in the soil. So now we're looking at between 70 and 80 pounds of loss on that field. So a 40% loss of investment from this farm. So now we've got to over-apply if we want to reach maximum yield potential. So this is just one example of how that Base Plus program can really help you guys hone in on that razor's edge of perfect nitrogen applications. But we've always got to think about the certain things of timing and placement and measurement. So that is why 360 offers 360 EQUI-FLOW. How many guys in here doing liquid fertilizer? Quite a few. How many guys orifice their liquid fertilizer? Same amount of people. Why do we orifice that? Consistent coverage across the toolbar, right? So when we think about anhydrous ammonia, most systems do not orifice. But 1 gallon of anhydrous ammonia can expand to 850 times that volume in a gas. So as a product with those properties, why would we not think about orificing and keeping it under pressure so that it is liquid ammonia all the way to the injection point? That's why we see variability with all these common conventional toolbars, because we rely on tank pressure and we're just pushing it out there without any metering except for right at the cooler. Once we move past that flow meter and that servo valve, it's up to the lines and the environment outside on what rate you're going to get to each knife. And Nowell will talk about that in a little bit. But what EQUI-FLOW is basically a high-pressure anhydrous system. We're going to bring in the anhydrous from the tank, and all we have to worry about for tank pressure is feeding the system itself. Once we're in the system, we're going to eliminate the vapor right away out of the filter tower here. It's going to be able to escape through the vapor tube. We're going to send the boiling anhydrous ammonia down through the bottom. As it hits this dam in here, it forces that boiling to move vertically. So now that boiling is going to get the rest of the vapor out of there. We can cool and condense more of that anhydrous, but as the liquid level rises in here, it's going to push on these floats. When the floats are up, these solenoid valves on the top are closed. As we start to get more back pressure in there and we restrict flow from the tank into the system, the liquid level inside the tower drops. When that float hits the bottom, the valves flicker open, relieve pressure, and we start the process over. What that does a very efficient process of getting vapor out of the system and puts 100% liquid ammonia over to the centrifugal pump. And from there, our system takes over and controls the pressure and the rate going to each knife, because we're orificing out to each injection point. And now, Nowell, I will turn that over to you so you could talk a little bit more about Gen 2, which is on the next slide, and you could talk about your bucket tests.
All right, thank you, Josh. Well, I'm excited to talk to everybody about anhydrous ammonia today and some of the data that we've been getting while testing this spring and last fall. So I about knocked the table over behind me. So when 360 started with anhydrous ammonia, Greg and Tim challenged the engineering team to come up with a system that would allow us to consistently and accurately measure the amount of anhydrous ammonia as applied out of each knife row. We know from being able to weigh tanks that typical bars using a rate controller and a flow meter are probably pretty consistent across the whole width of the bar. And if they aren't, they could be pretty easily dialed in by changing a meter calibration number in your rate controller. But what the unknown was the row-to-row accuracy. So as we started to develop the bucket test that you see here behind us, this is probably about our second or third revision to where we finally got to, and we're kind of constantly improving it as we go. But we start with an inductor tank for each row. It's an 18-gallon inductor tank, and we put a certain amount of water in there to match the tests that we're running. There are there's lines going down to the bottom of each one of these tanks that the anhydrous ammonia runs in during our test, and that line going to the bottom allows us to capture the anhydrous in the liquid so that it won't vapor off during the test itself. Each inductor tank is being held with a load cell that allows us to weigh the initial and final weights and progressively weigh the buckets during the test. And that allows us to actually see the difference in the amount of anhydrous applied during the test. Now, we've done quite a few toolbars, new and used, on the market. And I've got some data to share with you today that is really quite overwhelming for those of you that do apply anhydrous. If I can get the slide to change here. There we go. This first one that you're going to see is a vortex on a 24-row bar. Now, one thing I want to stress to everybody is that, the steel doesn't matter. The color of the steel doesn't matter. It's the application system itself. Traditional systems are heat exchangers or cooling systems that try to cool that anhydrous ammonia down below negative 28 degrees Fahrenheit, where it's going to start boiling and creating vapor. And from there, every elbow or reduction in the system can create even more vapor as it travels down to the knife row. And if you look at this data from this 24-row bar, we see a 25-pound swing, plus or minus, of nitrogen applied per acre. So that's a total of 50-pound variance across the toolbar, which is quite overwhelming for those of you that are trying to control their nitrogen program or are banding their nitrogen in the row. This is where, also as you can see on this chart, the EQUI-FLOW data in the black, really where EQUI-FLOW excels. Since we are pressurizing the anhydrous and then orificing it, we can guarantee ourselves a very equal distribution of that anhydrous down each row. With a typical bar or a typical system, by that I mean, you've got to contend with different hose lengths, kinks in the hose, dirty manifolds, just a number of things that can get into the system and really wreak havoc on your application rate and your consistency from row to row. When you're pressurizing the system with 360 EQUI-FLOW, it acts a lot like your liquid fertilizer, your side dress bars. You can pump it up to a consistent pressure, constant pressure, keep it at that pressure, and then orifice it at that rate for equal application down each row. Now I've got on the next slide here, I've got actually the exact same system, but on a 19 row. Both of these were brand new toolbars right out of the box. I think I can, yeah, I think that's the 19 row. So about the same results on this bar. We saw about a 25 pound plus or minus swing in applied rate over each row. Looking at used toolbars on a similar system to this, we'd probably see that number grow to about 35 pounds. It does increase a little bit. When we ran this test, we ran brand new anhydrous knife lines just to take out any inconsistencies that may occur from toolbar to toolbar. On the used systems that we did test, we cleaned the manifolds really well, put new lines to the manifolds to get rid of any air that might have been in the knife lines, just to eliminate that as an issue. And we were still seeing those 35 pound differences in rate. The last slide I have up here is a Dickie John system that you see parked out in the field behind us. And that bar we actually saw on this slide was a 40 pound deficit in one of the rows, which gives you an overall about a 55 pound swing, 60 pound swing row to row. So why are we seeing these rates? Are they believable? And why is EQUI-FLOW so much better? I think Josh and I have both kind of touched on this a little bit. But let's say you were applying and you were pulling a 1,000-gallon anhydrous tank. Probably start with, let's say, 850 gallons of product in there if you're filling it up, just part of the way. And you're applying it, you're trying to cool it down. Right out of that cooler, if you're running clear hose, you can always see that gas and that vapor moving through the liquid, like bubbles going down to the line, down to the knife. I think anybody that's applied with clear hose has seen that. But for a second, let's just assume that only 1% of that anhydrous ammonia going through there turns to vapor. Well, 1%, as Josh explained, anhydrous expands to 850 times its volume. There's about 7.5 cubic foot in a gallon. So that's about 960 cubic feet that you're trying to divide off equally from row to row. Makes it very difficult as that anhydrous moves down the knife lines, into the manifolds, and finally down to the knife. So with EQUI-FLOW, when we're running with clear lines, we actually don't see that bubbling in the lines. It stays clear right down to the manifold where we divide it off equally for accurate application. Now, one of the questions we get quite often is there is a lot of fall applied nitrogen around this part of Illinois, is how this system works in cold weather. And we do excel very well in that realm due to the fact that we are pumping the product past the system. So whereas traditional systems rely on that pressure drop of anhydrous ammonia from the nurse tank all the way down to the knife, we're only relying on that pressure drop from the tank into our system, and from there we're pressurizing the product up above nurse tank pressure and pushing it down to the rows. So we don't have to rely on that pressure drop all the way down to the row. Now I think we'll take questions at the end after I let Jason and Greg talk for a bit on SOILSCAN.
Thank you, Noel. So these guys kind of did talk about that base approach with the 360 EQUI-FLOW system, and that's a very highly efficient system. Anytime that we can ban nitrogen, where's that feedback coming from? All right. Anytime we can ban nitrogen in good placement for the corn crop system to access that is going to be a very highly efficient system. So in the next few slides, I'm going to allude to minimizing our NUE. So what that means is we're going to try to put on less pounds of nitrogen, but also still maximize the bushels that we're getting out of these fields. So we're going to show you how we're doing that. So when we go out, we're putting on a good base program, and then us at 360 here, we're taking a ton of nitrates, verifying what we have out in the field, and then also when we need to make that application as to best get our top dollar. Now, a very highly efficient way to do that is to actually have our own machine, 360 SOILSCAN. So that's giving us a very time efficient way of going back to the shop or even taking the sample in the field and seeing exactly what's out there. So if we have to, we can turn on a dime and go make that application. But just a quick question here. How many of you guys are using like a SeedStar system or a Monsanto FieldView system to verify your seed assets in the field? Quite a few of you, actually. So right now, we're actually, for a 200 bushel per acre farmer, he's actually spending $100 to $150 on seed inputs, and then anywhere from $50 to $100 an acre on nitrogen. Even some guys are pushing it up to $125, $150 for nitrogen cost per acre. So what we're trying to do in a sense is give you the ability to assess that nitrogen investment that you guys are putting out there every single year. So just like the field monitoring systems for your seed, we're able to go out and tell you how efficient was that nitrogen pass. And we're able to monitor that investment. Now, this next slide, there we go. This next slide is going to give you a few examples here of how we're comparing a few different systems. So Josh mentioned how we really want to push these base plus systems and how efficient the EQUI-FLOW system is because of time, because of placement and right rate. Now, we can be very efficient with a full load with that system, but for your top dollar, that's not what we want to do. So behind me is actually an example, and these are in the strips of corn behind the EQUI-FLOW setup here. And what we're showing is that 100 pounds of actual nitrogen with NH3 gave us 213 bushel per acre. And then right next to that is a one and done system where we put on our full load of nitrogen and only made an additional 7 bushel. So what that's telling us is this year our mineralization was extremely high, and we were able to maximize that 100 units. Now, why didn't we get that other 80 units to crank out a better NUE? Why didn't every single pound make a bushel of corn? And that's because of the access to the root system. So by that time, we couldn't carry on that 80 pounds, and maybe it even had to do with sealing in the environment that we had, but most likely that is because of plant access. Now, take it to the second row here, and we actually had this strip where we went in and used the proper base plus approach. So we went out there, and we actually put on 100 pounds with the EQUI-FLOW, and we came back at about V8, and we used our SOILSCAN system, and we found out that we didn't need to apply. We had about 25 units of nitrogen out there yet that we could utilize. So we waited a little bit, came back in 2 weeks, and we decided at V12 that we should pull the trigger. We were probably at about 13 part per million. A lot of times we don't like to go anywhere below 10 part per million because by the time you get everything up and running, your last field is going to be below 10 part per million, and we don't want to see that. The corn doesn't want to see that as well. So we went out in the correct timing, and we saw a yield check of 272 bushel per acre. So additionally in that field, we thought, well, maybe we should actually not use SOILSCAN and compare that system. So if you weren't nitrate sampling, you would actually go out in the field and maybe look for a deficiency. Just use like a color scheme. Maybe you're up in a drone or you're using modeling systems or imagery to decide whether to make that pass. And we actually were deficient for 2 weeks there. We would have never known if we weren't soil sampling and using 360 SOILSCAN, and that actually took 16 bushel off our top end. So there's there's a way that we can drastically hurt our NUE. Now, when we first brought in Y-drop in 2014, we saw some really crazy things. Before that, the industry was always telling us, you need to put on, for every bushel that you want in yield, you need to put on a pound of nitrogen. And now, when we got Y-drop and we started split applying at the right time, we found out that we could get to about a 0.9 NUE. And today, I'm standing in front of you, we've had amazing mineralization through June, and we found out that we can get upwards of 250, maybe even 270 on 180 units. So we're pushing that NUE down to 0.7, 0.8 range while still maximizing our bushel per acre. So we're not taking anything out of our profitability by being sustainable here. So this next slide is an example of 2015. So that was a total different year, and Greg Ury is going to go into 2015 versus 2016 with you guys and show you how he reacted with 360 SOILSCAN. But one thing that we always need to remember is sometimes we got to throw NUE out the door on efficiency and realize that there's top end to gain. So Mother Nature might have thrown a curveball at us, and we might have got 12 to 18 inches of rain in June, and we got to react to that. Last year, we ended up applying 150 to maybe 180 units at Y-drop, and that's just because we were trying to grab that top-end yield. So we wanted to keep our yields in that 230 to 250 and still maximize our profitability. So year to year, it's different. We might not always be able to have that low NUE that we were granted this year, but we still want to get that. We still want to maximize our profitability per acre. So what I talked about here was how we're using that in a system, how we're using 360 SOILSCAN in a system, and a couple other things that you can utilize 360 SOILSCAN for, whether you're a grower or a dealer, is just verifying your placement. So in that top picture to the left, there's actually an example of a grower who went out and put on anhydrous. He came back with a Coulter application right on top of that, and those bandits ended up 15 inches from the row in a 30-inch row system. So as we track that through the year, we've realized that root access isn't as high intensity as what our Y-drop system is in the below figure. So the below figure is where we actually put on an EQUI-FLOW past 4 inches from the plant. We came back with Y-drop, and you can see that the levels and the volumes of nitrogen are a little bit lower, but that's because we're getting better uptake with the plant. So our next picture there actually shows a couple examples of how we're assessing volumes of nitrogen out in the field. Are we going to be deficient? Does it warrant another nitrogen pass? And how we're following that through the field. And that third example is actually being able to use SOILSCAN for the right rate. So this year, that right rate was about 80 pounds with our Y-drop. If you did 80 pounds up front, it would have been 100 pounds with the Y-drop, and we did some studies with that. But this year, we actually followed the nitrogen curve throughout the field with our SOILSCAN, and then we came back at the right time. We put in our organic matter for that, and we actually got the correct rate. So that is an example of that. Now, one very important thing, and we cannot stress this to you enough, is being consistent with your polling practices. So just like if you're taking any other sample to the lab, we need you to be as consistent and strict with your nitrate polling practices as possible. So that goes from polling the samples throughout the field, using the same strategy to pull them, and then also preparation and shipping to wherever you may be going. You need to be consistent with that. So one thing that we do at 360 to try to keep that consistency is we actually have an app called 360 Yield Patrol. And what we're doing there is we're able to make sure we're getting to the correct spot and getting a representative sample of that field. And so what we actually use Yield Patrol for is being able to go to that spot multiple times. And you can also bring in shape files, making sure that you get into the soil type and everything like that, and that'll georeference you in the field. Now, once we're to the spot, we have another protocol. We actually use what we like to call the soil core board that we just actually, Greg will give you a good little demonstration here. We actually take the board and we throw it down in between the row. And why we're doing that is because we want to make sure that we're getting a good representation of what those roots may see down there. So we got a lot of guys that are doing a number of different practices pre-plant. He might be broadcast fertilizing, he may also be banding, but by pulling across the row in that fashion, we are actually making sure that we intercept the majority of that nitrogen while also getting a good representation of the unnitrified side. So once we pull the cores, we're actually, a lot of times we're taking a 1 to 12 inch core and then a 12 to 24. So you're going to assess the crop growth stage, and once we're about hip high, it's probably important to take that 12 to 24 because there is going to be some nitrogen access down there. So that's going to take digging a plant, assessing the root system, understanding in your own crop whether or not that can access that nitrogen down there. But once we pull the core, we're actually taking it back, putting it in a bucket, and we're actually trying to prepare that sample so that we can take out as much of those nitrate ions as possible. So when you guys send nutrient samples to the lab, they're actually going to take that sample and grind it up. No matter what nutrient you're looking for or trying to get analyzed, they're going to send it through a grinder. So those are pretty expensive pieces of equipment. So what we're trying to do is just take whatever you can. I know guys use putty knives. We actually fabbed up a little, an old bruised up Ninja blender and put it on a rod and run it on a DeWalt drill, and that mixes up the soil. But the biggest thing is trying to get those particles into a consistent size as possible. I know the clays are really tough. Josh, I think you actually mentioned that you freeze your clays and then you mash them in with a hammer.
Yeah, they did really
Yep. So if we can get those particle sizes down, we can pull those nitrates out a lot easier. So we have that. And then the other thing is handling. And Greg Ury is going to talk about proper handling of those samples once you get them out of the field. So.
All right, thank you, Jason. Yeah, so like Jason said, the proper technique of getting cores pulled is very, very important. Handling is also equally as important. So I've heard a lot of times from people who have SOILSCAN that they've ran a SOILSCAN result and then also sent it to a lab, and the results came back differently. So I kind of did the same thing this year where I was utilizing 2 labs and SOILSCAN. What I would do is go out on a Friday afternoon, I'd pull my sample, bring it in, get it mixed up well, and separate it out into 3 different samples. One sample I would go ahead and run through SOILSCAN. The other 2 samples I would freeze over the weekend. So I'd physically put them in my freezer and freeze them. On Monday morning, I would get up and I would box them up and take them in to ship them off UPS. So I did this for two different sampling periods, and you can see on the chart that SOILSCAN and Lab 2 came back very, very close both times. Lab 1 seemed to be elevated. So I thought, well, is SOILSCAN Lab 2 correct or is Lab 1 correct? So I brought in a 3rd sample. And the 3rd time I ran this, what I saw was SOILSCAN, Lab 2, and Lab 3 were very close. Does that mean that Lab 1's wrong? Maybe, right? So let me explain to you what the difference between Lab 1 and Lab 3 is. The only difference is the way I handled it. They're both going to the same lab. Lab 3, instead of putting it in a cardboard box frozen, I put it in a styrofoam cooler and shipped it off in a cooler. What I didn't tell you was Lab 2 took 2 days from the time I took it in to be able to get to the lab. Lab 1 was shipped the next day. So there was an extra 24-hour wait period between the time that it left me until it got to the lab. What we know is when we pull samples out of the ground, we introduce oxygen into that sample. As we introduce oxygen, we start getting microbes that are a lot more active. If we don't cool that sample down and slow those microbes down, what we've seen is we can really increase mineralization and nitrification very, very rapidly, causing some test results that are not truly what's going on in your field. So handling can have a big difference with the results we get. Last year, when we were here, I was pulling samples every morning, and I would run them each session. The first session, every day, came back around 12 to 15 part per million. The last sessions, I had them up to 52 part per million, the same sample. So that time can change that result and that information. So handling, if we want to know what's out there, is very important. If you're pulling a sample and you're waiting in the morning and you're not doing something with it until that afternoon, what I do is I carry a cooler around so I can start to get that temperature down in that soil. I do not want to leave it in my truck to where it's going up to 100 degrees and I'm getting some change. So handling's important. So we talk about base plus and the need to measure and the value of that. We know that nitrogen is very, very influenced by weather, isn't it? We can have increased loss or we can have increased mineralization. Here's a field looking at nitrate samples that I've taken in 2 different years, tracking it multiple different growth stages. Both of these are the same farm, both corn bean rotation, and both of them are 120 pound base rate. My goal is to come back in around V10 to V12 and apply 50 pounds to be able to finish out the year. But if you look at V6, both levels were about the same. In 2015, though, from V6 to V8, they went down. And if you look at the weather, track the weather on the right-hand side, you see that in 2015, the amount of rain I had was extremely high later on. So what we saw was in these fields was a huge amount of leaching and denitrification in 2015. My plan changed from what I originally wanted to do. I wanted to wait until V10 to V12. At V8, I knew right then I needed to do something. And instead of 50 pounds being the rate that I thought I'd run, I ended up bumping that to 90 pounds because of where I was at. We left strips out there in that field, and what we saw was a 30 to 40 bushel increase because of the ability to increase that rate. And the reason we knew how to increase that rate was because we were able to measure. 2016, completely different year. A lot less rainfall, almost ideal conditions with the exception of a couple dry weeks, but not near the loss. Huge amount of mineralization that we've occurred, so we were able to delay that application later into the season, and we didn't actually pull the trigger until about V14. Obviously, we don't have yield results yet from that field where we've done this, but doing some hand checks, it looks very, very good, and I think the potential is extremely high. So to finish it off, here's a picture of a field that we worked with last year in Iowa, that we did a one-and-done approach versus a base rate and then sample with SOILSCAN. As you can see, we did multiple different things where we had a SOILSCAN and then we did a plus and minus 25 to validate the results. But you can see that SOILSCAN was able to get us into that sweet spot where we were able to maximize that yield without over-applying a lot and without under-applying. So the key, one of the keys to being able to have a good base plus approach is to know where you're at and understand that each year is going to be different and the weather has a big influence on that. So generally we let you guys get off, but I think that we have 5 minutes. If you guys want to get up, stretch your legs, we'll be down here if you guys have any questions, and then we'll move you back to eat lunch.